Space looks calm. It is not. What we call the night sky is not an ocean of darkness. It is a vast battlefield of light, time, and illusion. Every single point you see, every shimmer in the black, is a galaxy, each one holding hundreds of billions of suns. And yet, the sky above you is mostly empty. That silence, that darkness, is the first lie the universe ever told us. Because if there are trillions of galaxies, so many that for every grain of sand on Earth, there are 10,000 worlds of fire, then why does the night remain dark? Why does infinity look so quiet? This is not just a poetic question. It is one of the deepest paradoxes in cosmology. Centuries ago, people believed the stars were holes punched in a celestial sphere, letting divine light leak through. Later, astronomers thought the universe was infinite, eternal, and evenly filled with stars. If that were true, the sky would blaze like the surface of the sun. But it does not. Something vast, must be stopping the light from reaching us. Our telescopes now see far beyond the Milky Way. We know there are roughly 2 trillion galaxies within the observable universe. 2 trillion islands of light drifting through an expanding cosmic ocean. Each one a city of stars, planets, black holes, and unknown forms of matter. And all of them are racing away from us. The farther they are, the faster they flee, as if reality itself is stretching apart. So what is the truth behind this impossible darkness? Why, in a universe overflowing with light, do we live surrounded by shadow? To answer that, we must go back, long before telescopes, long before science. Back to the first humans who looked up and began to wonder what all of this means. In the beginning, the universe was a mystery written across the night sky, and humanity had no instruments but its own eyes. Our ancestors looked upward and saw patterns, gods, and stories written in light. The Babylonians traced the motion of wandering stars and believed they were divine messengers. The Greeks imagined crystal spheres turning in perfect harmony. In India, the cosmos was a breathing being, expanding and contracting with each divine inhale. In China, the heavens mirrored the empire itself, a vast celestial bureaucracy, precise and eternal. Though every culture saw something different, they all shared the same impulse, to find meaning in the endless dark. The sky was not a question of physics yet. It was a question of existence. The sky was a god. Then, something changed. During the Renaissance, the universe began to shift from myth to mechanism. Copernicus dared to move the Earth from the center. Galileo raised a small tube of glass toward the heavens and saw that Jupiter had moons of its own, orbiting not us, but it. For the first time, humanity realized we were not the reference point of creation. When Newton followed, he wrote the rules that made the heavens predictable, the laws of motion and gravity. An apple falling and a planet orbiting were bound by the same invisible hand. The cosmos was no longer divine chaos. It was a system. For the first time, the heavens were governed by the same laws as the falling apple. But centuries later, another mind would shatter even that certainty. Albert Einstein changed the very idea of space and time. He revealed that gravity was not a force at all, but geometry. Massive objects bend the fabric of space-time, and the planets follow those curves. Time itself slows near gravity, stretching and folding like the surface of an invisible ocean. Reality became elastic. The universe was not a stage where things happened. It was an actor in the play itself. Suddenly, even time had a shape. And yet, there was still one question no one could answer. Had the universe always existed, or had it begun? The early 20th century brought an unexpected clue. A Belgian priest and physicist named Georges Lemaitre proposed something radical. The universe was expanding, not the galaxies moving through space, but space itself stretching between them. Soon after, Edwin Hubble used his telescope atop Mount Wilson to prove it. By measuring the light of distant galaxies, he saw that their colors were shifted toward red. The longer wavelengths of light stretched as space expanded. The farther away a galaxy was, the faster it receded. The universe, it turned out, had a beginning. From that idea grew the Big Bang, a moment when everything, space, time, matter, and energy, burst into existence from an unimaginably dense state. And the evidence kept arriving. We found the afterglow of that birth, the cosmic microwave background, a faint whisper of light still echoing through the universe, cooled to just 2.7 degrees above absolute zero. We discovered that the first elements, hydrogen and helium, were forged in those first minutes, and the expansion of space itself explained why galaxies drift apart like embers in a dying fire. By the mid-20th century, humanity believed it had finally written the story of the cosmos. A beginning, a set of laws, a future. The universe was no longer a mystery. It was a masterpiece of physics, predictable and elegant. But just as we started to believe the story was complete, the universe began to whisper something else, something that would change everything we thought we knew. Imagine peeling back the sky like a veil and discovering that every speck of darkness hides entire realms of light. This is what our age of astronomy has made possible. For most of human history, we could see only a few thousand stars with the naked eye. Now, our instruments reveal trillions of galaxies stretching across a cosmic horizon 46 billion light-years away. We have become witnesses to the structure of the universe itself. With Hubble, we first learned to see deep time. Pointed at what appeared to be an empty patch of sky, Hubble collected faint photons for days and revealed 10,000 galaxies in a region smaller than the width of your thumb. Each one was an ancient city of suns, billions of light-years away, their light older than humanity itself. That single image shattered our sense of scale. It told us that even in apparent nothingness, the universe was crowded with creation. When the James Webb Space Telescope launched, it expanded that vision again. With a mirror 7 meters wide and sensors tuned to infrared light, Webb could see through cosmic dust, revealing galaxies so distant that their light began traveling only a few 100 million years after the Big Bang. The earliest structures, once thought impossible to detect, now shimmered in its golden mirrors. We were looking at the universe as it was when it was a fraction of its current age. But telescopes are not just eyes. They are time machines. The light from those galaxies has taken billions of years to arrive. To look far is to look back. Every photon is a messenger from an era that no longer exists. The deeper we gaze, the younger the universe becomes, until the galaxies fade into the faint blue fog of the cosmic dawn. That is how we have built the most detailed map in history, a three-dimensional atlas of everything we can observe. Projects like Gaia, DESI, and the Sloan Digital Sky Survey have charted millions of galaxies, turning the night sky into a database. When scientists render this data, a breathtaking pattern emerges: the cosmic web. Imagine a colossal three-dimensional spider web, its filaments stretching across hundreds of millions of light-years. Along these filaments lie clusters of galaxies, bright nodes of matter, while in between, vast voids yawn, nearly empty. It is a map not of continents, but of gravity itself. The same forces that shape galaxies also weave the universe's skeleton. And yet, for all its beauty, this map is incomplete. Beyond a certain distance, light becomes too faint, too redshifted to ever reach us. Because the universe is expanding, there are galaxies that are receding faster than light itself, not through motion, but because space between us is stretching. Their light will never arrive. They exist beyond the observable universe, in regions forever cut off from us by the speed of cosmic expansion. In a very real sense, we will never see most of the universe. Even so, what we can see is astonishing. The cosmic microwave background, the afterglow of the Big Bang, gives us a snapshot of the universe when it was only 380,000 years old. It is the oldest picture ever taken, a baby photo of everything. The temperature variations in that ancient light are tiny, just a few millionths of a degree, but within them lie the seeds of every galaxy, every star, every living being that would ever exist. From that faint ripple pattern, the universe wrote its future. Today, we can trace that evolution from the Big Bang to now with remarkable precision. We can measure the rate of expansion, the distribution of matter, and even the mysterious forces pulling everything apart. We have built a story that feels complete, a timeline from birth to present. But in the quiet margins of our data, subtle whispers remain. They suggest that this story, beautiful as it is, may not be the whole truth. The universe might be hiding something, something that should not exist. For decades, cosmologists believed the map was complete. The standard model of cosmology fit almost everything: the cosmic microwave background, the expansion of space, the distribution of galaxies. The numbers lined up too perfectly, almost reassuringly so. But then, faint cracks began to appear, small disagreements, strange signals, patterns that should not exist. The universe, it seemed, was not as obedient as we thought. One of the first anomalies came from something deceptively simple: measuring how fast the universe is expanding. There are two main ways to calculate this rate, known as the Hubble constant. One method measures nearby supernovae and Cepheid stars. The other uses the cosmic microwave background, the leftover light from the early universe. Both should give the same result. They do not. One gives 73 kilometers per second per megaparsec, the other 67. A small difference, but large enough to shake the foundations of cosmology. If your ruler gives you two answers for the same distance, you have a problem. Scientists called it the Hubble Tension, and to this day, no one fully understands it. Something in our model, or our universe, is off. Then came the galaxies that should not exist. In 2023, the James Webb Space Telescope peered into the cosmic dawn and found massive, mature galaxies appearing just a few 100 million years after the Big Bang. According to our understanding, there was not enough time for so much matter to clump together, ignite, and form stars. Yet there they were, huge, bright, and ancient. It was as if the universe had skipped a few chapters in its own story. Those galaxies should not have had enough time to assemble. The data was real. The models strained to explain it. But anomalies did not stop there. As our cosmic surveys grew larger, new structures appeared, immense walls and arcs of galaxies spanning billions of light years. The giant arc, the Big Ring, and the Hercules Corona Borealis Great Wall, formations so vast they seem to defy one of cosmology's most sacred principles, that on the largest scales, the universe should look the same everywhere. These structures were too big, too coherent to fit inside the limits of statistical randomness. In theory, they should not exist. Yet telescopes kept finding them, glowing faintly in the darkness like the fingerprints of something ancient and unseen. And then came the invisible mysteries, dark matter and dark energy. For nearly a century, we have known that the stars we see account for only a tiny fraction of what is out there. Galaxies spin too fast to be held together by their visible mass. Something unseen, something heavy, must be providing extra gravity. We call it dark matter, but after decades of searching, through underground detectors, cosmic rays, and high-energy collisions, we have not found a single particle of it. The silence grows heavier each year. It is as if the universe is playing a trick, giving us effects without causes. And above even that, an even stranger force, dark energy, the driver of the universe's acceleration. For a while, we assumed it was constant, a simple cosmological term. But new observations suggest it may not be fixed. It might be changing with time, slowly rewriting the fate of the cosmos itself. If true, that would mean the energy of the vacuum is not stable. The fabric of reality could evolve. Each of these puzzles alone might be manageable. But together, they whisper something unsettling. Perhaps our entire framework is incomplete. Perhaps the universe we have modeled is only an approximation of something deeper, more fluid, and less predictable than our equations can capture. At some point, you stop blaming the measurements, and you start questioning the model itself. For most of modern cosmology, one model has ruled them all. It is called ЛCDM, the Lambda Cold Dark Matter Model, and it has been our cosmic compass for nearly half a century. It describes a universe made of three ingredients: ordinary matter, cold dark matter, and dark energy, represented by the Greek letter lambda. Like a recipe, it explains nearly everything we observe: the shape of the cosmic microwave background, the formation of galaxies, the expansion of space. It is elegant, predictive, and powerful. But perhaps it is only an approximation, an equation that works on paper, but fails to capture the universe's full complexity. In the ЛCDM model, just under 5% of the cosmos is made of ordinary matter, the atoms that form stars, planets, and us. Roughly 27% is dark matter, invisible but gravitationally dominant, the scaffolding upon which galaxies form. And the remaining 68% is dark energy, an enigmatic force that drives the accelerated expansion of space. On paper, it fits perfectly. It reproduces the cosmic web, matches the CMB data, and aligns with the way galaxies cluster. For decades, it seemed unbreakable. But beneath that precision lies an uncomfortable truth. We do not actually know what any of the main ingredients are. We call it dark matter, but no one has ever detected a dark matter particle. We call it dark energy, but no one understands what it truly is, whether it is a property of space itself, a new field, or an illusion created by something even stranger. Even the cosmological constant L may not be constant at all. When we calculate its theoretical value from quantum field theory, it overshoots reality by 120 orders of magnitude, the worst mismatch in the history of physics. Something, somewhere, is deeply wrong, and the more we look, the more cracks appear. The horizon problem. Why does the universe look so uniform in every direction, even in regions that have never been in causal contact? The flatness problem. Why is the geometry of space so perfectly balanced between open and closed? The missing satellites problem. Why do our simulations predict far more small galaxies than we observe? Each question chips away at the model's certainty. A theory that once felt invincible now begins to feel incomplete. Some scientists compare ЛCDM to a beautifully tuned instrument, one that plays the right notes, but not the whole song. It works within a narrow range of conditions, but outside of that range, the harmony breaks down. We may be seeing only the shadow of a deeper theory, one that unites gravity and quantum mechanics, one that explains why the universe expands and how it began. Einstein gave us the curvature of space-time. Quantum physics gave us the uncertainty of matter, but between them lies a frontier we still cannot cross. The standard model of cosmology is a triumph, but it might also be a bridge, a structure that takes us part way across the cosmic river, but not to the far shore. It explains what happens, but not why. It describes the expansion of the universe, but not the engine that drives it. It tells us that dark matter must exist, but not what it is. It paints a portrait of the cosmos that is stunning, but maybe not final. It is like a beautiful equation written on paper that we have never seen carved into the real world. If the ЛCDM model is only an approximation, then what lies beyond it? What if the story of the universe is even stranger, even grander, than we have dared to imagine? This is where cosmology begins to shift from measurement into imagination. When equations begin to tremble, imagination steps in. Speculative cosmology is where science meets wonder, a frontier where data thins out and the human mind fills the gaps with mathematical dreams. If the standard model of cosmology is incomplete, then something must exist beyond it, something that explains the cracks we have begun to see. For decades, physicists have proposed bold new visions of the universe, each one strange, each one beautiful, and all of them still unproven. Yet together, they reveal just how vast the possibilities may be. The first great idea to challenge our cosmic story was inflation. In the 1980s, physicist Alan Guth proposed that in the first instant after the Big Bang, the universe expanded faster than the speed of light, driven by a burst of negative pressure in the quantum vacuum. This brief moment of exponential growth, called cosmic inflation, would solve several mysteries at once. Why the universe looks the same everywhere, why it appears flat, and why tiny quantum ripples became the seeds of galaxies. Inflation is more than a theory of expansion. It is a story of how chaos became structure. Yet the equations that describe inflation also allow for something far stranger: eternal inflation. In this scenario, inflation never stops everywhere at once. Some regions of space stop expanding and form bubble universes like ours, while others keep inflating forever. Each bubble could have its own laws of physics, its own constants, perhaps even its own dimensions. Together, they form what scientists call the multiverse, a cosmic foam of endless creation. Our universe, then, might be just one bubble among countless others, drifting in an infinite sea of space-time. It is speculative, but mathematically motivated. Another theory goes even further, suggesting that the Big Bang was not the beginning at all. In loop quantum cosmology, space and time themselves are quantized, made of tiny, discrete loops that cannot be compressed beyond a certain limit. When the universe becomes too dense, gravity turns repulsive, causing a bounce instead of a singularity. Before our Big Bang, there may have been another universe collapsing in on itself. When it reached its limit, it rebounded, giving birth to ours. The universe could be an eternal rhythm of expansion and contraction, a heartbeat of creation echoing through infinite time. Sir Roger Penrose proposed a different vision: conformal cyclic cosmology. According to this idea, the universe is a chain of aeons, each one beginning where the previous one ends. In the far future, when all matter decays and black holes evaporate, only massless radiation remains. Without mass, there is no meaningful scale for time or distance, and the geometry of the universe becomes identical to the moment of another Big Bang. In that way, the end of one cosmos becomes the birth of another. The arrow of time does not vanish, it loops. Our universe, Penrose suggests, might carry subtle imprints from the aeon that came before it, echoes of a cosmic ancestry written in the microwave background. And then there is string theory, perhaps the most ambitious attempt to unify everything. It imagines that the fundamental particles of nature are not points, but tiny vibrating strings, whose resonances create all forces and matter. In this picture, our universe could be a three-dimensional membrane, or brain, floating within a higher dimensional space. Entire universes could exist parallel to ours, separated by imperceptible dimensions. A collision between two brains could even trigger a new Big Bang, igniting a new cosmos in an endless, higher dimensional arena. Each of these theories is speculative, but they are not fantasies. They emerge from real mathematics, from the same equations that describe gravity, quantum mechanics, and the geometry of space-time. They stretch our imagination, but they also reflect a deep human truth. When confronted with mystery, we dream bigger. Whether the universe is one bubble in an infinite sea, a heartbeat that bounces forever, a cycle of aeons repeating endlessly, or a brain drifting through higher space, each idea points to the same question. If there are countless universes, countless beginnings, what does that make us? No matter which model turns out to be true, they all must face the same question. How does it all end? At the edge of what we can see, the universe fades into silence. Beyond that horizon, light has not had enough time to reach us. It is not that those regions do not exist. They are simply too far away, receding faster than light as space itself expands. To look out is to look back, and at the farthest edge of our vision, we glimpse the universe as it was only moments after its birth. That boundary, 46 billion light-years away, is not a wall of matter, but a wall of time. Beyond it, the cosmos continues unseen, perhaps forever. Inside that observable bubble lies everything we can ever know, every galaxy, every atom, every beam of light that will ever touch our eyes. Imagine it as a sphere of awareness, an island of visibility floating in an infinite sea. As time passes, this horizon does not shrink, it grows. New regions come into view as light from farther distances finally arrives. But at the same time, the expansion of the universe pulls other galaxies away faster than light can chase them. One by one, they slip beyond our reach. The cosmic shoreline of visibility moves outward, but the ocean of darkness grows even faster. It is a haunting paradox. The more we learn, the more we lose. Far in the future, billions of years from now, even the galaxies outside our local group will vanish beyond that horizon. Their light will fade, stretched into invisibility by the relentless expansion of space. The universe will grow emptier, colder, and darker. Stars will exhaust their fuel and die. White dwarfs will cool into black lumps of carbon. Neutron stars will fade, and even black holes will slowly evaporate, releasing their mass as faint radiation over unimaginable timescales. Eventually, only photons and subatomic whispers will remain, spread thinly across an expanding void. This is the heat death of the universe. the final equilibrium where energy and matter are evenly distributed, and no new structure can form. No light, no motion, no change. The lights go out. Silence. If you could stand in that far future, you would see nothing but darkness. No galaxies, no stars, not even the faint memory of what once was. The cosmic background radiation itself would have stretched beyond detectability. Time would still exist, but nothing within it would move or evolve. The universe would persist, but without purpose, without contrast, without sound. In that eternal quiet, even the concept of time begins to lose meaning. And yet, there is a strange beauty in this ending. It is not a violent collapse, but a gentle fading, like the last breath of a vast organism falling into sleep. The universe does not die with a scream, it drifts into silence. Every atom that ever formed a star, a world, a mind, will eventually dissolve into radiation, carried outward by an expansion that never ends. It is a solemn truth. Entropy wins. But within that truth lies the miracle that it ever began at all. Perhaps the universe will end in darkness. Perhaps it will bounce, or birth another cosmos from its ashes. Perhaps it will dissolve into quantum foam, where new universes flicker into existence like sparks from dying embers. We do not know. All we know is that the edge of reality is not just a place. It is a moment, an encounter with the limits of what consciousness can perceive. And so, we are left with a question that is larger than science, older than philosophy. Where does this all lead? Where does it leave us? A fragile species on a small world, in a universe that will one day forget we were ever here. In the face of eternity, our existence might seem microscopic, almost meaningless, a brief shimmer of awareness in an ocean of time. Yet that is only one way to see it. There is another, that through us, the universe has finally learned to look at itself. Every neuron firing in a human brain, every act of wonder when we gaze at the stars, is the cosmos becoming conscious of its own story. The atoms that once drifted inside a collapsing star now form the thoughts that ask where they came from. We are not separate from the universe. We are its voice, its memory, and its question. Across the vastness of time, the universe created structure from chaos, chemistry from dust, and consciousness from starlight. From that improbable chain, we emerged, a species capable of understanding that there are trillions of galaxies, capable of mapping their dance, and capable of imagining what might lie beyond them. It took 13.8 billion years for hydrogen to learn how to wonder. That fact alone transforms insignificance into something sacred. Our smallness is not a flaw, it is the price of awareness. The miracle is not that the universe is vast, it is that we can feel awe within it. The truth about trillions of galaxies is not just about scale, it is about meaning. For every one of those galaxies, filled with uncountable stars, the odds that consciousness should exist at all are nearly zero. Yet here we are, in one corner of one galaxy, asking questions that reach across them all. Perhaps that is the hidden symmetry of the cosmos, that awareness and vastness must coexist. The larger the universe becomes, the more extraordinary consciousness appears. In that light, the darkness of the cosmos is not emptiness, but contrast. Without it, the stars would not shine. Without uncertainty, there would be no discovery. Without impermanence, there would be no beauty. The universe is both infinite and fleeting, and so are we. The purpose may not be to last forever, but to witness, to feel, to ask. Every measurement, every equation, every telescope aimed at the sky is an act of faith, Faith that knowing is worth the effort, even when the answers slip beyond reach. Perhaps the point is not to solve the universe, but to participate in it, to be the brief moment when matter learns to dream. When we gaze at the galaxies, we are not just looking out, we are looking in, seeing the reflection of what we are made of and what we will return to. We are the universe remembering itself, briefly illuminated by thought, before returning to the dark that made us. We may never know the full story of the cosmos, but there is something quietly extraordinary about being here to ask. In every question we whisper to the stars, the universe whispers back through time, "You were part of this all along." So now, as the final light of this story fades, we return to the same sky that began it all. Above us stretch the silent witnesses of creation, trillions of galaxies, drifting like lanterns across a sea of time. Each one is a library of forgotten histories, a record of what once burned, collided, and bloomed in the darkness. And somewhere among them, on a small blue world orbiting an ordinary star, a fragile species dared to ask how it all began. That question alone makes the silence less lonely. Perhaps that is the quiet truth of the cosmos. That meaning is not written in the stars, but in the act of looking up. The galaxies do not need us to exist, but existence becomes beautiful because we choose to see. We have mapped the past, measured the light, and dreamed beyond the horizon. Yet the greatest discovery remains this: that wonder itself is a form of survival. The universe will go on, expanding into the unknown, but so will curiosity. As long as one mind somewhere in the dark still asks why, the story continues. Every telescope we build, every question we dare to ask, is another heartbeat of that story. So when you step outside tonight, look up. Somewhere, light that left its home before Earth even existed is arriving just now, meeting your eyes for the first and only time. That is the universe saying hello across eternity. Until the next question and the next impossible light in the dark, keep looking up.